This is lesson 25, implicit differentiation. Before we actually talk about the differentiation of an implicit equation, we have to be clear on what the difference is between an implicit versus explicit equation. So there's some examples of implicit equations, and you'll notice that they have a variety of x's and y's all mixed together. An explicit equation is where we've solved for one of the variables, and typically what we do is we solve for y. And we write y in terms of x because x is our input, which then allows us to evaluate and find our output of y. So an explicit equation, we have solved for y, but an implicit equation, we still have x's and y's can all mix together. And that's the difference between implicit and explicit. We've been solving, or not solving, but finding derivatives for explicit equations. We have not done any derivatives of implicit equations, and that's what this lesson is about. So just to have a better understanding, when we've taken the derivative of an explicit equation, we've started with an explicit equation, such as this. And you would know to use the power rule for this, but let's look at the notation more carefully. We're taking the derivative with respect to x because this equation has been solved in terms of x. But really what we are doing is we are taking the derivative of each and every term in that equation. We're taking the derivative with respect to x of y. We're also taking the derivative with respect to x of 3x squared. And we're taking the derivative with respect to x of 4x. And we're taking the derivative with respect to x of 5. So every single one of these terms we are taking the derivative with respect to x. And when the term itself is an x, we can take that derivative explicitly and we use the power rule. So we know that the derivative of 3x squared is, we bring the 2 down, so we have 3 times 2 times x to the first. But what we did is we took the derivative of x dx. And it's really the chain rule, if you think about it, that we took the derivative of x squared, a squaring function, and we put the 2 in front and raised it up 1 to whatever was inside, which was x. And then we would take the derivative of the x with respect to x. Here we would take the derivative of 4x, which is going to be 4, and then the derivative of this function that was to multiply by 4, what was inside of it was x, so we took the derivative of x dx. This last one is derivative of a constant, and always the derivative of a constant is 0, so there's nothing here. But what happened to what's here on the left? Well, let's first finish this part up where the dx, the derivative of x with respect to x, that would just be 1. So each one of those in yellow becomes a 1, and we simplify, and we end up with 6x plus 4. But on the left-hand side, we still have that dy dx because we can't actually take the derivative of y when it is respect to x. So that notation is telling us what we did. And so we leave it in that format, and this stays here, and this is saying this is what we did. We took the derivative of this y with respect to x. Now, we have to look at the chain rule because this idea of implicit and explicit derivatives has to do with chain rule. So looking at the chain rule, if I've got this nested function, this function f that has 3 functions really inside, it's a composite, we know that we start on the outside and we start with the derivative of the outside and we keep moving in. This is really what's going on. We're taking in terms of x and we're taking the derivative of the whole thing, which means we're taking the derivative of f in terms of g, because I'd say take the derivative of f and leave all of this alone. Then you would take the derivative of g and leave everything inside of that alone. So that's the derivative of g in terms of h. And lastly, we take the derivative of h in terms of x, and all of that equals the derivative of the function in respect to x. And why does that happen? Because similar to dimensional analysis where you can cancel units that are alike, these two things actually cancel out. And so this dg and dg, they cancel, the dh and the dh cancel, and what you're left with is the derivative of f with respect to x, and that's the derivative of f with respect to x. And that's what we end up saying when we take the derivative of that entire function. And so this was the way we've written it before. We used the prime notation, and we multiplied all these three things together to give us the derivative of the whole function with respect to x. So that's the chain rule. And the key here is what's happening with all of this notation and this kind of dimensional analysis. So when I'm going to take the derivative of something that is not in terms of x, but I want to take the derivative of it, and I'm saying, but I want to take the derivative in terms of x, I can use this idea of dimensional analysis and say, well, if I take it in respect to whatever it is, so if this was in terms of y, so I had some y's in here but no x's, I had y's, I'd say, oh, then I'm going to take the derivative of this thing in terms of y, since that has y's in it. But if I multiply it by dy over dx, I'm going to get back to this. So this is equivalent, and that's how we use the chain rule to help us with explicit differentiation, or implicit differentiation. So in this case, I wanted to take the derivative of y squared, but I want to take it in terms of x. Since this does not have x's in it, I'm going to write it in terms of y. So derivative of y squared with respect to y. That way I can take the derivative of y squared. But I have to multiply it times dy over dx, so that when this cancels, I do end up still with this derivative of y squared with respect to x. And the derivative of y squared, when it's taken with respect to y, is 2y. And so that was, that is right here, this is the derivative of y squared with respect to x. This would be the answer. Now, notation gets a little bit wiggly, or not wiggly, it gets congested because you're writing all of these fractions dy dx. So that's one of the reasons why we have this simpler notation, this y prime. It's just a way to write things a lot neater. Similarly, if I said derivative of f with respect to x, I would say f prime. When I'm using the prime notation, I always have to be using it in terms of the same thing. Every single one of those primes has to be with respect to the same variable. If I took the derivative of x with respect to x, well, dimensional analysis is no different than dividing numbers, that I've got the same thing dividing into itself, so that's going to equal a 1. So here's a relation. And while this is x in terms of y, it's not solved for y. And so if I want to take the derivative with respect to x, I'm going to have to do implicit differentiation. I take the derivative of every term. No problem here on the left because this term x is in terms of x, so I can take that derivative. The derivative of x with respect to x is just 1. But over here, I'm taking the derivative of y squared with respect to x. And since this isn't x, I have to use the chain rule. And so I take it with respect to y and multiply it by dy over dx. And in the end, I have this answer. Y prime means dy dx. If I want to solve for y prime, meaning I want to solve for dy dx, which we know is the slope of the tangent line, I'm going to have to divide both sides by 2y. And when I solve for the y prime, dividing by 2y, I get this equation. Now, this equation will give me the slopes of any tangent line to this relation. So if I had a point on here, say I had the point, I could have a 4, 2, because if my x was 4, one of my y's could be 2. So if I was saying the point 4, 2 is on this relationship, what's the slope at 4, 2? I would use the 2 from the y here and say that my slope is 1/4. So this would be a way I could find any slope at any point on this relation. Here's a problem you would see like in a homework. It says find the slope of the tangent line to the relation x squared plus y squared equals 25 at the point 3, 4 on the relation. Well, we should recognize that that's a circle with a radius of 5, and what I'm asking for is in this circle I have the point right here, which is 3, 4, and the tangent to that, I want to know the slope of that line. So I find, to find the dy dx, since this is not solved for y, I have to do implicit differentiation. and I take the derivative of both sides. When I take the derivative of both sides, I'm going to take the derivative of each and every term, but I am taking the derivative with respect to x, because the slope is the change in y over the change in x, and I can take this derivative here because it's in terms of x, which is going to be 2x, but this one I'm going to need the chain rule. And so I end up with 2y times dy dx. I'm going to solve for dy dx because I want to solve for the slope. That was what I'm here for, to find the slope. So I subtract 2x from both sides, I divide by 2y, and I end up with the equation for any slope of any tangent to that circle would be negative x over y. So now I'm going to use the point that was given, 3, 4, and plugging in 3 for x and 4 for y, I get the slope at the point, 3, 4, is negative 3/4. And that is, and if we looked at this, and if you could zoom in, you'd go down 3 and over 4, and you'd find out, oh yeah, that is the slope of that line. So here's another one. This is not a circle, that's just some relation. Find the slope of the tangent line to the graph of this equation at the point 7, 2. Once again, we're going to take the derivative with respect to x, the derivative of each and every term. And so for the first one here, I'm going to use the chain rule, meaning I'm going to take the derivative with respect to y of this and then multiply it by dy dx. But this one here, this is a product rule because I have two different variables being multiplied. I'm going to have to utilize the product rule. So here I use the chain rule, and here I've got the first times the derivative of the second. To take the derivative of y, we would use the chain rule. I take the derivative of y, which is 1, and then I was saying, oh, I multiplied it by dy dx, plus the second times the derivative of the first is just 1. So this is the derivative of x times y using the product rule. And distribute this negative and then collect like terms and solve for the slope, solve for dy dx. So here I rewrote the equation. I had a y, so I added it to both sides. It would have been a negative y, and I added it to both sides. Now these two terms have dy dx, factor it out, divide by that 3y squared minus x, and we have the equation right here. This is the equation for any slope of a tangent line to the relation. We had the point 7, 2. You plug in 7 for x, 2 for y, and evaluate. And this is the very specific slope of the tangent to the relation at the point 7, 2. Okay? Next one. This one doesn't say for a specific numeric slope. We just want to know the generic, the equation for it. So we're going to take the derivative of this, implicit differentiation. And so we're going to take the derivative of each and every term with respect to x. And so we write it in that fashion. You see that this one's going to be the chain rule. This is going to be the chain rule. And everything's a chain rule here. So derivative of x squared is 2x. The derivative of 2y cubed would be 2 times 3y squared. But we are left with dy dx, which we're going to write in this fashion. The derivative of 4y with respect to y would be 4. And then we have to write, well, we did the derivative of y with respect to x, so we write y prime. Now we're going to subtract 2x from both sides, factoring out the y prime, dividing by that. And lastly, I don't like this negative up here, so I'm going to take it and distribute it to all the terms in the denominator to write what I think is a neater answer so that my numerator is positive. And this is the equation for the slope of any tangent to the given relation, otherwise known as y prime.